Hello everyone, my name is Shreyan Goswami and me and Zaid are going to give a short presentation on the topic of model compression techniques including student and teacher paradigms. So in this presentation we will be talking about ROSITA, which is refined BERT compression with integrated techniques. Let's find out what is BERT and why do we need to compress it. So BERT is a bidirectional encoder representations from transformers. Basically, BERT is a language model which improves the efficiency of NLP tasks, and it helps to understand a sentence, what is the meaning of it, and also the semantics of it. But the main problem is that BERT is trained on a massive amount of text data, and it is having numerous hundreds of millions of trainable parameters, and that is why to train the complete model in a local setup may be impossible, and because of its very high computational cost and expensive computation. So the main goal of this paper or this research paper is to compress the model but to keep the accuracy more or less optimized or maximized. So here we can see that ROSITA or refined BERT compression with integrated techniques uses multiple compression techniques together and is integrated carefully to maintain optimized accuracy. So there are many other compressed BERT versions like tiny BERT or mobile BERT, but ROSITA is 7.5 times smaller than BERT and it maintains a accuracy of 98.5% on 5 tasks of the GLUE benchmark. And what is GLUE? GLUE is General Language Understanding Evaluation. They give some benchmarks where we can evaluate or analyze our natural language understanding systems. And so here they are giving a performance of 98.5%, which is quite good. And in this model, ROSITA, there are 3 compression techniques that are used: wet pruning, low rank factorization, and knowledge distillation. Now the main point that might come in our mind is how to integrate these compression techniques in one model. So the researchers tried different parameters, they played with them like the different ratio of compression, and then divide the knowledge distillation process into multiple stages, and then playing around with the pruning frequency and the learning rate schedule. So here is the complete pictorial representation of what we are going to do with the BERT model to compress it. So here on the left part of the diagram is the BERT model, and the colored boxes are the wet matrices which we are going to compress to decrease the size of the model. And on the right side are the techniques that we are going to use to compress BERT. Here, as we can see on the left side, it's written L multiplied with, which means in BERT there are L such kind of transformers, as we can see, and at the end we have a classifier to classify it. If we go to the next page, here we can see that there are L identical transformers, as I have said. These wet matrices are the query matrices, key matrices, and the values matrices. Now in this self attention block there are H paralleled attention blocks which gives one unified value WAO at the end. Now in these H paralleled attention heads we are having WQI, WKI and WVI for each of these self attention heads. So we are going to compress each of those, as we will see later. It's just the background of the BERT architecture. As we can see, the self attribute is attributing these X of WQI, WKI, WVI. Attribute of QKV is the softmax of QK transpose divided by root of DK. Now X is the layer input which is coming after combining with this embedding matrix. And now let's go to the next block, which is the feed forward neural network. where we are using a ReLU function. As you can see, this one is a ReLU function. Max of 0 and x WFI plus BFI. Now the B are the bias matrices. And finally, from all these transformer modules, we are finally calculating the cross entropy loss, which is negative of y star log of softmax of z. Now y star is one hot vector of the ground truth label and z are the predicted logits. Now let's go on with the first method of compression that is used. Before that, I'll say that before that we are not going to use all the L transformers for training. We will take the first L dash transformers to decrease the number of transformers, which will obviously compress and decrease the size of the model ROSITA. So in weight pruning, we will try to understand the importance of each and every neuron. Now how to understand that? We will try to see if I eliminate a weight from the weight matrix, how is it going to affect the loss function. As you can see here, this S value is just trying to calculate the neuron importance. So here its expectation x is one of the data from the dataset D. So here I am trying to understand that how the loss function is changing with one of the weights in the weight matrix in the ith row and the jth column. So if S value is quite high, we cannot eliminate that neuron or that weight connection, because that weight is having quite an importance in the neural network. So we will try to find those neurons which are having least importance, and then we can prune them from the network, as you can see in this diagram. And for one step pruning, we average the first order Taylor expansion, which is this one, and scores over the training set. And for iterative pruning, we accumulate the scores over the training steps before the between pruning operations. Okay, and now let's see what is low rank factorization. In low rank factorization, we are simply performing singular value decomposition on the tokenizing embedding matrix. As we can see in this diagram, the WEMB is the tokenizing embedding matrix, and so we are going to perform low rank factorization on weight matrix of weight embedding matrix. So we are performing singular value decomposition on it, and we are getting three matrices, multiplication of three matrices. Now sigma in between here is a diagonal matrix, and the diagonal entries are the eigenvalues, the sigma i's, and the value of the sigma I represents the importance of that column in the matrix. So if the sigma values are quite low, we can eradicate those columns, which leads to a smaller size of the weight matrix. And here this V is the vocabulary size. Now this will lead to decrease of the size of the matrix, this matrix, embedding matrix. Now the last technique that we are going to integrate for compression is the knowledge distillation. Now what we are doing in this knowledge distillation is that first we are going to see the predicted loss, where ZT and ZS are the predicted logits of teacher and student respectively, and the predicted loss is negation of the softmax of predicted logit of teacher multiplied with log of softmax of the predicted logit of students. Then after the predicted logic is transferred from the teacher to the student, the next thing that we are going to transfer is the hidden states, and the teacher's hidden states are learned by minimizing the mean squared error, where loss of the hidden state is given by the summation of mean squared errors of the x value. Now x is every time the input that is going for each of these blocks. Now in knowledge distillation, what we are going to do is we are decreasing the value of WAO and WQKV, which is here. The knowledge distillation is working in the self attention block, and the weight pruning is working in the feed forward network block, and the low rank factorization is working on WEMB. So this is all about the techniques that they have integrated in Rosita. Next, going on forward, my friend Zaid will um, explain about the uh, general experimental setup for this Rosita model.
Uh, Hello everyone, my name is Zaid Ahmed Khan, and now moving on towards experimental setup. In this paper, they have used blue benchmark dataset, which consists of dataset like COLA, SST2, QNLI, QUP, MNLI, and in evaluation metrics, we have used Matthew correlation for GOLA and for accuracy for the other dataset. Uh, the formula for Matthew correlation is given here. We calculate three quantities N, S, and P, which are in terms of Tn, 2 negative, 2 positive, false negative, and false positive. And finally, after that, we can calculate the Matthew correlation MCC, which is done for classification task, and this is its formula. And during implementation, we have in the paper they have tried four different learning state and use Adam optimizer and tried two batch sizes of 32 and 64, and they have used data augmentation techniques to mitigate the problem of loss in accuracy due to pruning uh, during knowledge distillation. And to give you an idea about how the dataset look, below is given an example of QNLI dataset, which consists of two sentences and with a label corresponding to each ID. There can be only two labels, entailment and non-entailment. Entailments mean if the second sentence can be implied from sentence 1, it is called entailment, and vice versa for non-entailment. This is a classification data set used in BERT. So, coming on to a key finding which was present in this paper is they tested a variety of BERT architecture. As you can see, H equal L, and these are the dimension height and length, width. Length means here width, and different kind of dimension, the depth, R, etc. On all the benchmark data set which I have uh, told earlier. So on experiment, they found that the model architecture C, which is the deepest architecture, uh, it was performing the best. L equal 8, you can see its length is the highest, and from this we can say that different parts of bird layer should be uh, should be pruned in a different way to get the best accuracy. So these are some four different knowledge distillation schemes which were presented in the paper. The first scheme is one step tuning plus one stage knowledge distillation. In this, we have tuned the BERT model from the teacher to the architecture C, which I have told earlier, the most depth one architecture which was giving the highest accuracy to the at dimension. And then we have done knowledge distillation, that is forcing the distilled model to give prediction like the teacher model. uh, Knowledge distillation using loss function which Shayan has discussed earlier. And second scheme is one step tuning plus two stage knowledge distillation. In this, we have initialized one bird based student model with untrained weights, and then we have forced that bird based student model, which have the same dimension as a teacher trained model, to give prediction like the teacher model. And after from that student model, we have done pruning to get architecture C, and then done knowledge distillation again during that tuning task. And this hidden distillation means the doing the training and distillation of hidden layers. And prediction distillation means doing the distillation of prediction layer, that is outer final layers. And third scheme is doing iterative width wise pruning and two-stage knowledge distillation. The first step remains the same, making a bird based student model from teacher using knowledge distillation. And then we have done iteratively the pruning which we were doing earlier. Uh, what I mean by iteratively is that we are doing pruning for say some few step and for few intensity, and then we are doing again knowledge distillation. Then we are doing pruning and doing knowledge distillation, that is forcing the model to give prediction like the teacher model. And we keep on doing that this again and again until we get a constant accuracy. So this is iterative width pruning. IW means we are doing pruning in width direction, that is reducing the width of the bird base model. And the fourth scheme is IW and ID pruning, iterative width and depth pruning, plus three-stage knowledge distillation. In this, again, we are creating a bird-based student model from a teacher model using a knowledge distillation, and then first we are doing iteratively depth pruning, uh, iterative pruning in depth direction. That is, for each layer, we are just changing the depth and doing pruning in that layer. And yeah, prediction knowledge distillation and tuning recursively. And then we are after we got a constant value, we are doing tuning in width direction and knowledge distillation again uh, iteratively until we get a constant value. So these are some of the results which are present of multi-stage knowledge distillation. uh, you can see bird base and bird student and architecture C, which we have got earlier. uh, so as I was saying, we are using iterative tuning. So there's come some important parameters which are tuning frequency, how fast we are doing tuning and coming back to knowledge distillation, and learning rate schedule. So in this experiment, we have used two kind of learning rate schedule: constant learning rate schedule and linear learning rate schedule. And we have uh, kept a constant amount of steps in batches. And these are the graphs that we have got on in the paper that I mentioned. uh, we can see that the blue one, the pruning step, which for which it is 1%, it is generally above at the end of the iterations. So, based on the experiments, we found that the optimal pruning frequency is between 1 to 10% of training steps. And if we keep the pruning frequency too fast, the performance drop to too much. And as you can see, like the 80% at some point, the accuracy is dropping too much. And if we keep it too slow, then there will not be enough time for the model to learn during knowledge distillation. Not much step would be left for that part. And the effect of learning rate schedule, we found that the constant learning rate schedule is best suited for helping the model to recover after we have done the pruning. And linear learning rate schedule slows down the recovery process, so it should not be used after the pruning step. We can use it in the initial training steps. So this is a comparison with the existing methods. Uh, one, the first one being Dynabird. It utilizes task-specific knowledge distillation, and it also uses structured pruning, like doing the pruning of attention head intermediate output layers. Limitation of it is it does not compresses the embedding metrics which we are doing in this paper, and also the task specific knowledge distillation made the model uh, specific to some specific task and not a generalized one. In Tiny Bird, they uses pure knowledge distillation, in which they have used knowledge distillation for pre-training as well as for task-specific fine-tuning. The limitation is it relies on knowledge distillation and not other methods like pruning and factorization are used, which could be very helpful in getting even more simpler model. But Tiny Bird is a very good example of proving that only pure knowledge distillation can also help in reducing the architecture size by a large amount and without compromising the accuracy by much, so showing the power of knowledge distillation. And in Mobile Bird, they have used task agnostic knowledge distillation, which means they have used a generalized version of knowledge distillation, not making it specific for a similar task, and kind of use a bottleneck architecture of Bird, which is in the starting layer, it is the width is more, and in the final layers, the width is less. So the limitation of this is the teacher model that is used, bottleneck architecture, is 2.7x larger than that used in this paper, which increases its complexity and also the time which is required for knowledge distillation. And coming to Mini LM, they have also used task agnostic knowledge distillation, which I told earlier, and self attention distillation, in which they are using key query and value like kind of distillation on all these three matrices. And the limitation of this is it focuses only on knowledge distillation and does not utilizes pruning or factorization method, which we have done in this paper. And then last one is ladder BERT, which uses weight tuning, low rank factorization, and knowledge distillation. Uh, Limitation of it is the pruning is very unstructured, and data augmentation technique is not used during knowledge distillation to mitigate the drop in accuracy which we generally get in knowledge distillation while doing the pruning. So these are the result which we mentioned in the paper against the competitor which I have told earlier, and ROSITA outperforms baselines with similar parameter budgets. You can see that this one is for ROSITA, and these are the competitor. In almost every task, Rosetta outperforms except for QQP data set, and Rosetta is 7.x smaller than the Bird model and nearly maintains 98.5% of performance on Glue benchmark data set. So these were the findings present in the paper. Thank you for giving this opportunity.